Hello, my name is Pran Mukherjee. I'm a technology architect here at InterSystems, and today I'm going to talk to you about some performance testing with the tools we have available. First, I'll do a little introduction on the tools, and then a quick demonstration, not live, of the results, then analysis of the results so you can kind of get an idea of what to look for when you run your system yourself. You'll understand at the end of this how to do hardware stress testing with the tools we have available. You'll find out where to get the tools and understand the output. For the introduction, we have two sets of tools technically. One of them is the monitoring tools, and one is the stress test tools. The monitoring tools here that we'll talk about are SAM, System Alerting and Monitoring, which is relatively new. There will be links to other documentation on it later. It's used to create a real-time iris monitoring dashboard, and it runs in Docker with 5 containers. So you need to have Docker running. System Performance, which was formerly called pbuttons, is built into Iris, and it's a configurable background monitoring tool. Yape, yet another pbuttons extractor, you can see that the name is a little old, is used to turn the output of either pbuttons or System Performance into graphs that are easy to read and understand. That also runs in Docker in a single container. It can monitor both Iris statistics and hardware statistics like CPU usage or memory. The system stress tools, the one we'll be talking about today is perftools.ranread. It's used to stress test database block reads via the view command. So it doesn't pull up a specific variable, it just pulls up a random block out of a database. You can have multiple process threads, which are limited by license. There are no delays between reads, so it continually runs as soon as the CPU is available, and it can run from any namespace. We also have additional tools to test write and CPU that will not be covered by this talk, but just so you're aware that this is not the only one we have. Those will be available once we get them into a condition where they're all sort of similar. Each of them works slightly differently right now, and the ranread tool is the most robust at this point. Eventually, they'll all have similar capabilities, such as timed runs, run from anywhere, multi-threaded, etc. You download the tools from either Docker or the GitHub location listed here. And before you start anything, you must have a working Iris distribution and Docker running. For the quick demo, first we'll talk about prepping everything. You want to get sysstat on your system in order to get iostat output from System Performance and Yape. The command is here, and you can see how it's run. You don't have to have this, but if you want to have the iostat output, you need to have it running on your system. The command listed is just for Red Hat, but you can just Google it, and there's other ways to do it for other operating systems. To prep your system for ranread, you need to first create the database, and to do that, you want to have WDU sync IO off. By default, it's off. So if there's nothing listed in your iris.cpf file, it's off, and you don't need to do step 1. If it's in your iris.cpf file and set to 1, you're going to want to turn it off before you start up your session. Once you start your session, do the system obj load, and for whatever path you've saved the ranread tool to, and just load it up. And that's what the command would look like. This is the key piece here. You want to create the namespace and database for it. Ranread does it itself with a setup command, but it takes quite a while. The arguments are whatever directory you want it to be in, kind of parallel with the rest of your databases, or if you're testing the run of a specific device, make sure that that directory is on that device. And then a name for the database, we just usually call it zranread, and then the size. The larger the database, the less likely any of the random block reads is to pick one that's already been read and is in cache. So bigger is better for that. But bigger also takes longer to make. For 500 gigabytes, it takes about 15 to 20 minutes on a pretty beefy system. All you'll see when it's creating it is that creating 500 gigabytes database in directory. You won't see any of the rest of this. It'll just look like it hung. So you want to wait until it gets all the way through, and then at the bottom, it'll tell you what to run next to actually run the system. You can see that it's creating the database if you look at it in SAM. If SAM is running and pointed at your instance, you can see that the CPU is active while it's building this database. The final preparation you want to do is make a testing mode in System Performance again, this is optional because there are already about 5 or 6 of them built in, but you want one with good granularity, every 1, 2, 3 seconds. This is a very lightweight tool, but the more granularity you get, the better information you'll have on your system. Here's the command to run, or to create a profile for a 5-minute run, 2 seconds, sampling every 2 seconds. And you can see that the 2 is an argument, but the 5 minutes is not. It's 2 seconds times 150 iterations of that 2 seconds, which is 300 seconds or 5 minutes. So don't try to put in like 2,5. And then again, optional, if you want your WD Sync IO on, if you had it on before, you got to, at this point, stop Iris, edit the CPF, and restart and start over again. Because you only want to do this if that's the way you're going to run your system once all this testing is done. You want to test the system in the same condition that you'd actually be running it. Some considerations include the threads that you run RANRead for each take up a license. So if your key involves 100 licenses and you have 50 threads, you're fine. But you don't want to go over maybe 95 in that case, because if you use up your license limit, it'll crash, it'll hang, and you won't really be able to recover easily. There's a bunch of cruft left over in the system. Also, each thread will try to take up as much CPU as it can on one core. So it won't saturate like one thread per core, but it'll get close. And finally, the iterations are not compute time. The iterations take however long they take running flat out. So to figure out how long it takes, you'll need to do some experimentation on your system. It depends on how fast your system is. With the tools listed, you'll have instantaneous monitoring via SAM and a full analysis with good granularity via System Performance and YAPE. Now, again, this is a full throttle, gas, all the way to the limit, not a realistic run for like 5 people running on your system or whatever. So to run the tool, you first want to run System Performance. In the %sys database, you do System Performance. Then you run the command that it listed when you created the RANRead database, the ranread.run. The directory there is whatever directory you made your database in. The first number there, the 10, is a number of threads, and the second is a number of iterations. These are just guidelines for the system I was running. In general, you're probably going to want to test it first with a few threads less than you have cores, just to make sure that the system's all working. When it's running, you'll see dots on the screen, and you'll see the status of the run in the management portal under System Operation Processes. I'll show slides of both of that. After you've done your quick test, you'll want to add some threads to push the system harder and/or add iterations to make it run longer. Sometimes you're going to want to run for an hour or 10 hours or 24 hours to make sure that it doesn't just fall apart after running flat out for a little while. That's not what we're going to run in this demo, but that is a viable mode to run it in. Here's what it looks like. You go to %sys, pick your profile for System Performance, and then run the command. When it first starts, it'll show this creating 10 processes in the background. And it's just basically making the processes. If it hangs, that's all you'll see. It'll never go beyond that normally. But once all the processes are created, then it'll run all of them, and it'll start the waiting to finish ... 1 dot every second. That number of dots, that's around a 20, 30-second run. It doesn't take a lot to run it for just a few seconds with 100,000 iterations on this system. If you're running it for hours, days, it'll obviously have a lot more dots, and you may want to just turn that into a job instead of a do command. Once it's done, you'll see the average response time, and you want that to be low, and you'll see the calculated IOPS, and you want that to be high. The IOPS are for the aggregate of all the threads, not just for a single thread. Oh, one other thing. You can see here with the System Performance, it says it'll be done in 420 seconds, even though it was a 300-second run. That's because it takes 2 minutes to collate the results. When it's completed, you'll just see a really long file name with a .html at the end of it. So this is what it looks like when you're running RANRead with the parameters I showed. And this is what it looks like in the Processes tab. You can see 10 threads that say perftools.ranread.1, and they're all in the run state. If they're missing or if they're hung, something's wrong, and they'll go away once the job is done. This is what it'll look like in SAM. Now, this is what it looks like when you're doing a 30-minute test that I ran with the command listed here. 2, 4, 6, 8, all the way up to 50 for each number run with 200,000, with that number of threads and 200,000 iterations, and then hang for 15 seconds so you can see the spacing. You don't need to do the hang part if you don't want to. It was just for illustration purposes. In SAM, this is a little choppy because SAM has about a 15, 20 second time slice. It doesn't read continuously. So that 15 seconds was essentially just to make sure that there is a drop. Otherwise, you won't even see it. To analyze the results, you're going to want to collect all the data. Now, you can collect the stuff from, in terms of IOPS and response time via the export command built into RANRead. It'll just output it to a file that you can read. I just graphed it in Excel. And you can see that as you add more threads, there's more IOPS and there's more latency. The former is good, the latter is bad. But that's just how it goes. In a realistic case, both of those lines will rise, and eventually the IOPS will saturate. I did not push the system far enough to actually see it kind of asymptote out in this run because that would have taken a lot more threads. Again, you can check that your system performance run is complete by looking in wherever you have your P buttons or system performance output set to go and look for an HTML file. That long name here, 3par shardmaster, Virt Summit 2020, date, process number, and then 5 minute 2 second, that's how long the name is. Then you run Yape on it from wherever you have Docker running, assuming you have pulled down the Yape container. And the quotes here, if you want to copy and paste, make sure that they look correct on your screen. Sometimes it turns to like the open quote, close quote, so it doesn't really work correctly. You'll note that I have --mgstat, vmstat, and iostat here. That just tells it what outputs to create. And let's take a look at some results here. The data blocks we're looking at, there's some explanations for each of them on these links. And again, the results will depend on the system capabilities and configuration. So there's no good or bad. This is just kind of an idea of what you'll see. This is from iostat. You can see the reads per second. Our KB per sec is kilobytes read per second, which looks very similar to this. You can see each block, or each peak here is one of the runs. 2 threads, 4 threads, 6 threads, 8 threads, and so on. And you can tell here it does not start to get ragged. It doesn't start to saturate until well after 8 threads. It does slowly start to kind of asymptote out as to the reads per second, but it's not fully flat by this point at all. The queue size says how many requests there are in the queue, and you want to see that grow because that basically means that you're running the system pretty flat out and that your system is scalable enough to be loaded under high I/O. The R awaits, these are a large part of the response time, and they sort of scale with the response time, but they're not the complete amount. 0.17 to 0.28 or so is what we see on this graph. And on the graph a few slides ago, you could see, I think it was 0.18 to 0.35 or thereabouts. This is a big portion of it, but not all of it. And the more threads you have, the more weights you're going to have because you're saturating your CPU. Glow refs are not really supposed to be affected by this, as I understand it, but because this is reading directly from a view command, but in this case it is, and you can see that it looks pretty much identical to the other graphs that we've shown. So if it's wildly different, that might indicate something strange. If you do see effects from global references, you want to see it track with the other graphs, such as the blocks received from an input device. Again, it looks very similar. This is the CPU with more granularity than you could see on SAM. You can see instead of just a quick spike, you see it growing, growing, growing. It's around 80 to 90% once you hit 8 threads, which corresponds to the 8 CPUs. It really kind of pegs the CPUs around 12 to 16 threads. and then it starts kind of widening the time it takes. As the CPU is running flat out, it just takes longer to get those 200,000 iterations. This one's an odd one. This is the wait percentage, the percentage of CPU time spent waiting on I/O, which used to be part of the idle time prior to Linux 2541. You can see as it goes up to 8 threads, it rises. But then as the CPUs start to get more and more saturated, it drops because the CPUs are spending more of their time doing something and less of their time waiting for I/O. So that's what that drop-off means. We do have other tools, and you may also want to use the same methodology while you're running your system yourself and look at things like write speed or CPU speed. For writes, you want to look at these metrics here, the WD phase, the write daemon phase. Is it getting stuck? In the past, I've seen it get stuck on phase 8 every single time it runs, but only for a brief period of time, and that's okay. As long as it comes back to 0, you're okay. The queue size, does that empty out correctly? Running some of the tools that we have, or under a heavy load, it tends to kind of look like a sawtooth as the write daemon queue fills up, and then when the write daemon runs every 80 seconds, it drops down close to 0 or sometimes at 0. It doesn't have to be at 0 every time, as long as it gets close. The widge, again, every 80 seconds, it should activate write and be done. Physical writes, the same thing. That should go on the same 80-second cadence. You should see it spike and then go back to 0. Journal writes, they scale with your global updates. So those two graphs, they correspond to however many writes you have. So if you're doing a heavy write load, you should kind of see it like at whatever level, and then if you stop it, they should both drop down. But the two should scale kind of together. For IOStat, you can look at write await, writes per second, and write kilobytes per second. Do they make sense? And again, it really depends on your system. The key takeaway from this, again, is that there's no right or wrong answer. You need to look at what you expect from your system and what you see in these results and see if they look reasonable. If you're expecting 2 million global updates from a write test and you're getting 10, something's wrong. Or if you're trying to, if you have 8 CPUs and you're not saturating them by the time you have 100 threads running, again, something's wrong. So, I mean, not necessarily wrong, but there's something worth looking at. So everything depends on your system and usage conditions. And this runs a system as fast as it can go. There's no waits, there's no delays, there's no nothing. Once it receives one block, it looks for the next one, and so on and so forth. So it's not a regular use case. If it runs under these conditions, you can see what the system's capable of. And as long as that's greater than or equal to what you expect to see under real conditions, you're in good shape. In general, you'll want to use these tools fairly regularly, even when there's no problem, especially system performance. We recommend that you run this kind of on a daily basis just so you have a baseline to look at that you can compare to when something goes wrong. SAM is good just to have a real-time eye on what's happening. Just kind of glance at it, look at your dashboard, say, everything looks good, and you're done. It takes 10 seconds. You can do it once a day. In the management portal, the process list and other tools are useful for if you see something wrong, you can dig into it a little further. For next steps, the session Dev 007 has more details on SAM. As I said earlier, it's a new tool that we're just rolling out in the last few months. So if you want more details, you can look at that talk. You can always look at learning.intersystems.com for more information on essentially any of these things. And here's a few additional web pages on SAM, system performance, and Murray Oldfield's doc page on Yape, which a lot of this demo comes from. So that's all still relevant, and you can look at that as well. You can connect with me via email if you have any questions, or on LinkedIn. And thanks for your time.